Okay, I actually want to know how the hell we come up with that first solution. Because yesterday we said, if I've got a first one, I can get more. So here are some examples of the kinds of equations I want to be able to work with. And I'm really very, very particular here. I am only looking at equations that have constant coefficients. So there's no x squared, there's no whatever of x. It's just number times y double prime, number times y prime, number times y. Now here's the best part. Uh, Out of the three equations that I put up here, two of them are second order, one of them is first. I know how to solve this one. That's a linear first order differential equation. It's 100% solvable with an integrating factor. All I have to do is rewrite that. Y prime plus 5 half y equals 0. And then that's set up linear. And if it's linear, my integrating factor is what? X. T, whatever, right? So if I wrote X there. So now I have e to the 5 halves x y prime plus 5 halves e to the 5 halves x y equals 0. Yeah, this is a product rule. Perfect. I get e to the 5 halves x y quantity prime equals 0. When I integrate, I get a constant over here. So I end up with y being c e to the minus 5 halves x. Perfect. Chef's kiss. By the way, this equation is also separable. You could have done it by separating as well. But let me think about this for a second. I integrated e to the integral of p of t because that's what you told me to do with integrating factors. It's what I told you guys to do. It's what the textbook told me to do. It's the way to do it. Yeah, because it makes this left-hand side look like a product rule, and I'm good with that. But that's not going to work for the second order equations. The second order equations are absolutely not going to be solved the same way. But when I look at this equation right here, and I think to myself, hey, what about algebra? Let me make an assumption for the moment. Suppose my solution looks like e to the number x. That's what we got, right? E to the number x. So let me make that assumption even for the second degree equations. Let's go with this one right here. So I'm going to say this is my y. What's y prime? What's y double prime? e to the rx. All right. Plug those into this equation. And I get r squared e to the rx minus r e to the rx minus 6 e to the rx must be 0. Everything in there has an e to the rx, right? Factored out. What are you left with? No dying, please. Ah, not just any polynomial, a quadratic. And take a look at that equation, that quadratic right there. I know an exponential is never 0. E to the thing is never equal to 0. So the only way for this whole expression to be 0 is for that quadratic to be 0. Now compare the quadratic that is in parentheses with the original differential equation with the star next to it up at the top of the screen. Oh, wait a second. I have a second derivative, r squared, minus this first derivative, minus an r, minus 6 times the 0th derivative, minus 6. Look at that circled equation. Let's play the same BS game. Where I have a y prime, I'm going to put an r. Where I have a y, I'm going to put a 1. This equation here becomes 2r plus 5 equals 0. What's the value of r that makes that work? Mother... What are the values of r that make this work? Remember, the differential equation is y double prime minus y prime minus 6y equals 0. I would like you to pick one of these roots and either use e to the 3x or e to the minus 2x. Pick one and plug it in. Does it work? If you use e to the 3x, the second derivative is 9e to the 3x. The first derivative is 3e to the 3x. So I'll have 9e to the 3x minus 3e to the 3x minus 6e to the 3x. That's 0. If I use e to the negative 2x, the first derivative is minus 2e to the minus 2x. The second derivative is positive 4e to the minus 2x. So I have 4 minus negative 2 minus 6. That's 0. It worked. When I have constant coefficients, my dealing with a second order differential equation just became dealing with a quadratic equation. When I have a second order differential equation, solving that with constant coefficients, numbers in front of all of those powers of y, derivatives of y and y, became solving a quadratic equation. Because I got this, I now know the solution to this differential equation is C1 e to the 3x plus C2 e to the minus 2x. I got both pieces of my fundamental set of solutions in one step by finding this. This equation right here is called the auxiliary equation. Some textbooks call it a characteristic equation. Sound familiar, linear people? And that makes these characteristic values. The same freaking terminology. Differential equations have eigenvalues. And that means that I can look at any differential equation. Here is a second order differential equation. It's got constant coefficients. What is the corresponding auxiliary equation? We turned this differential equation, had this auxiliary equation. So now I've given you a new differential equation. Just minus 9. Quick, what are the roots of that equation? People, this is a differential equations class. I'm asking you to do an algebra piece solving a quadratic equation. This should be a little faster. Come on. What are the roots? What are the numbers whose square is 9? I'm done. And that means that the solution here is y equals C1 e to the positive 3x and C2 e to the negative 3x. As soon as I have the roots of my quadratic, I'm done. But I rigged this problem. Same question. What's the problem this time? But my quadratic in this case is ugly, right? The quadratic equation, 12r squared minus 5r minus 2. Can you factor that? Maybe. But if not, whip out the quadratic formula. It does actually factor. I did cheat. I had it factored beforehand. But if you didn't know, you whip out the quadratic formula. This gives me r equals negative 1/4. This gives me r equals 2/3. I get the same result out of the quadratic formula. 5 plus or minus the square root of 25 plus 96 over 24. Wait a minute. 25 and 96 is 121. Square root is 11. So that's 5 plus or minus 11 over 24. If I subtract, I get negative 6. Negative 6 over 24 is negative 1/4. If I add, 16 over 24 is 2/3. So the solution to my differential equation and I'm done.
Will it ever matter which one comes first?
Nope. You change which one's C1 and which one's C2, put them in the other order. It's beautiful. All I have to do is solve a quadratic. But sometimes solving a quadratic isn't enough. Find the auxiliary equation and solve it.
R minus 2 squared.
Uh-huh. Which means I only get one root, right? I get r equals 2. It's in there twice. It's a double root because it's squared. But if I use e to the 2x and e to the 2x again, what problem do I have? It'd be the same thing, wouldn't it? And that won't be independent. I only have one solution instead of two. I need two solutions. It's a second order differential equation. I should have two linearly independent functions to make my fundamental set. I only have one. However, go back to your notes from yesterday. I have one. How do I get a second? That's what we did yesterday, isn't it? That disgusting looking integral, right? That was a nasty mother. Before you do that, this was the example I did yesterday. I'm cheating. You know the answer to this problem. You know what the second function is because we did this already. But you're right, no, I need to do that bug ugly integral thing. So let's do that. Y2, so Y1 is e to the 2x. Y2 is e to the 2x integral of e to the negative integral of p. P. P is this number, right? Over y1 squared dx. Oh, I forgot the dx there. I got it right there. Okay, good. What do we get on top? What do we get on the bottom? That means that's the integral of 1. What's the integral of 1? X. And that's exactly what we got yesterday when we did our reduction of order setup. You know the best part? There's absolutely nothing magical about the number 2 in this problem. It just was the root in our auxiliary equation.
Why wouldn't there be plus C
Where?
after we take it from 1?
Oh, because I can assume in this case that C would be 0. If I put a plus C here, it's going to get multiplied by e to the 2x, right? Isn't that in the other function, y1? So I don't need to worry about it. That's the dependent part. I can pull that off. So here's an interesting result. I do the quadratic. If I get one root, the next one comes from reduction of order. But I'm going to short circuit this. When I have constant coefficients, this integral always, always, always works out to be the integral of 1. If I have a repeated root, then when I do reduction of order, every time, I'm going to get an extra x. Period. When I have constant coefficients, it always works out this way. Ready? My solution is y equals C1 e to the minus 4x plus C2 x e to the minus 4x. Whenever I see a repeated root, that's what's going to happen. Because I have constant coefficients. This is rigged. This is rigged really effing hard. Rigged.
Say, we know, we know it's this because it's a repeated root
Because we have constant coefficients in the original equation here. This only works because of the constant coefficients part. Everything we're doing today is screwed if we have an x floating around outside one of those y's or y primes or y double primes. I can only make these immediate algebraic moves when I'm working with constant coefficients. Questions? So I solve my quadratic equation. If I have two roots, it's e to the first root plus e to the second root with constants. If I have one root, it's e to the first root and then x e to the first root. But wait, there's more. I told you taking complex variables would be helpful here. All right. Mother, what do I do with this? It should be e to the number x, right? What the does that mean? I'm going to rewrite this just a little. A formula from Leonhard Euler related complex numbers to trig functions. It turns out one of my favorite things is to say e to the I theta is cosine theta plus I sine theta. Now we actually can prove this using power series. No, Mia, I'm not going to. But it turns out to be an absolutely true fact, which means when I write e to the I times 3x, the way to think of this is to think of this as cosine 3x plus I sine 3x. That's disgusting. But I'm going to be a nice guy. Because there's another root, right? There's minus 3i. Yes, there's minus 3i. If I do e to the minus 3x, well, then I get cosine of minus 3x plus I sine minus 3x. The following question is a trig question that you probably haven't thought about in years. When I have a negative inside a cosine, what happens to it?
Saying it's like a weird formula.
I'm actually going to, yes, it's a weird formula, but it's actually a very simple weird formula. Think of the graph of cosine. If you just draw a cosine of x, wait a minute. From the middle, it's the same on the left and the right, yes? The left side is exactly the same as the right side. The negative side is exactly the same as the positive side. This minus sign vanishes. Cosine of minus 3x is the same as cosine of 3x. It's an even function. That's a term we used in algebra decades ago for some of you, right? I remember that. We talked about even functions once. What about sine? Think of the graph of sine. Graph of sine first goes up and then comes back down, right? So when I go to the left, it goes down and then back up. So it's going the opposite direction. What's up on the right is down on the left. So if I go to the left, that's the opposite of what I have on the right. The minus sign jumps out front. They're conjugates. Now, they still have I in them, and I hate having I's in the result for a real differential equation. There's nothing in that differential equation that wasn't a real number. I used 1 and 9. There shouldn't be any I in the damn result. Linear independence. If I take the Wronskian, it turns out if I add these two together, what happens with the sine terms? And if I subtract the two, the cosine will cancel, right? So I really don't need the I. I just need the cosine part and the sine part. The correct final solution to this is y equals c1 cosine 3x plus c2 sine 3x. Whenever I have a complex result, I can break it up into just the cosine part and just the sine part. Let me do another one because this is going to take some getting used to. My corresponding auxiliary equation, 3r squared plus 2r plus 1 equals 0. Now, I am about to prove myself to be a complete pain in the ass. This isn't going to factor. So either you're going to have to do the quadratic formula, or you're going to have to complete the square. I actually think in this case, completing the square is better. But I'm a sick mother. So let me walk you through that. First thing I do is divide by 3. And I take the 1/3 and I put it on the other side. Now, when you do completing the square, you take half the number in the middle and square it. What's half the number in the middle? Squared is 1/9. Notice that on the right, what I have is a negative number. When I add those, common denominator, I'll get -2/9. But on the left, I'm going to get r plus 1/3 squared. And this is why I think this is easier. Because now, when I take the square root, I get square root of 2 over 3i with a plus or minus. There's my complex number. Take the square root of this, the negative becomes the I. Move the negative 1/3 over, and I get negative 1/3 plus or minus √2 over 3i. That's my root. So I want to use e to the negative 1/3 plus √2 over 3i x. Blah. Why did I like this? You can do the quadratic formula. I'm not going to be upset about that at all. But I think completing the square shows me the complex number in a better way. I don't have to worry about simplifying the square root, the 4ac and the 2a, taking it to its lowest form. I get that automatically from here. That's gross. I'm going to break it up into 2 pieces. I'm adding. When you're adding, you multiply 2 e's, right? Adding in a power means multiplying bases. The I is only in the second part. So that gets split up into the cosine and the sine. So this gives me a cosine of √2 over 3x. And it gives me a sine of √2 over 3x. But those also have this part with it. And there's my solution. When I think of a complex number, I think of the 2 pieces, the part that has the I and the part that doesn't, as separate. I'm going to call them A and B. So every complex number looks like A plus or minus BI. When we have a complex number, we're going to get e to the AX cosine BX and e to the AX sine BX. Yes, sir.
We don't care about the negative.
No, because remember, that was what we did in the previous one, where it turns out if we add them, the negative goes away. Yeah, it all disappears. So it turns out that the 2 independent pieces that I want are just the cosine piece and the sine piece. Hey, wait a minute. You ready for the crazy part? I know, this whole thing is crazy. Cosine of number x. What's the graph of that look like? Wobble, 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 right? But e to the minus 1/3 x, what does that look like? It's e to a negative, right? It's the graph of e to the minus x. E to the x goes this way, so e to the minus x goes this way, which means we're getting smaller as we go off to infinity. We're vibrating and getting smaller. This is a vibration that is slowing down. Didn't we talk about a process that would do that over time? This has got a real application. It's got a huge set of real applications. Questions? When I solve a quadratic, I either get two different real numbers, I get one repeated real number, or I get a complex number, set of complex numbers. In every one of those three equations, I know what's going to come out as the solution to the differential equation. Every time. As long as I can solve a quadratic, I can solve a second order differential equation with constant coefficients. If I gave you initial values, you could solve for C1 and C2. The first thing I'm going to do is find the corresponding auxiliary equation. And solve that. And that tells me my solution is y equals C1 e to the 5t plus C2 e to the negative t. By the way, you want to use x, I don't care. If I want to solve for C1 and C2, I plug that in. Y of 1 equals 0. So I put in 1, I get 0 equals C1 e to the 5 plus C2 e to the minus 1. That's disgusting. To do y prime of 1, I need y prime. What's y prime? So y prime of 1 equals 2 means that 2 equals 5c1 e to the 5 minus c2 e to the negative 1. And now I can use two equations in two variables to solve for C1 and C2. So this just became, instead of a differential equations problem, this just became two different algebra problems. Solve a quadratic, solve a set of simultaneous equations. Walk away. No calculus required, no integration, none of that shit. This is algebra. Only when I have constant coefficients. Guess what? Higher order differential equations work exactly the same way. With the same restrictions. If I see a repeated root, I'm going to get that extra x. If it repeats twice, I'm going to get an x and an x squared. If I see complex roots, I'll get cosines and sines. If I see real and, this has got 3 roots, right? I could have 1 real and 2 complex. It's still going to work the same way. By the way, in this case, I did cheat. R cubed minus 5r squared plus 3r plus 9 equals 0. I have not got the foggiest idea how to factor that. So how do I find out where that's equal to 0? Graph it. Use the x-intercepts. Plug it into Wolfram alpha. Tell me where it's equal to 0. I get r plus 1 times r minus 3 squared, which means I have a repeated root. R equals -1, R equals 3, repeated. So I get C1 e to the minus x plus C2 e to the 3x plus C3 x e to the 3x. Ta-da! I just turned solving differential equations into algebra. And I will be the first person to tell you that factoring equations is not trivial. But if I've got a graphing device, I'm done. It is quite feasible that the algebra of solving the equation is the most disgusting part of this process. So when in doubt, if you don't know how to factor the damn thing, graph it. Throw it into Wolfram alpha, throw it into Desmos, and you'll get the roots. What I do with those roots after depends on whether they are distinct real, repeated real, or complex. And complex roots are real applications. That slowly diminishing vibration idea is something I want to have happen in real systems and engineering. That's the real world. I don't want my shock absorbers to keep bouncing me as I drive down the street. I want it to smooth out over time. That's what I'm after. I don't see you people tomorrow. I see you on Friday for question and answer day. So I'll see you then. Right? Friday is doing